Okay, screen is visible.
Yes, sir.
Okay. So previous class we discussed space vector modulation for 3-level inverter, right? So in this class we will discuss. Huh? Yes.
PPT is not visible, sir.
Okay. So now it is visible.
Yes, sir.
Okay. So previous class we discussed the space vector modulation technique for 2-level inverter, 3-level inverter, right? Okay. So in the space vector modulation technique, we observed that so there will be some deviation in the capacitor voltages. So that deviation can be solved by some extent by using the small vectors, right? So by using p-type and n-type small vectors, so we can reduce that neutral point unbalance to some extent, but it cannot be completely eliminated. Okay, so to completely eliminate this neutral point, this capacitor, to completely balance these two capacitors, this one and this one, so we have this, we need to connect some external circuit. We need to connect some external circuit. So this will be it will be something like this. So we need to connect some chopper circuit. So for that, okay, so the circuit will be like this. Okay, so this is the external circuit. So that is used to balance the capacitor voltages, right? Say it is say this voltage is VD1, right? And this voltage is say this voltage is, for example, this is VC2, and this voltage is VC1, capacitor 1 voltage and capacitor 2 voltage. So assume that this switch is SU upper switch and this is SL lower switch. Okay, so this is a simple chopper circuit, right? A simple DC-DC converter circuit. This is simple DC-DC converter circuit. The switching signals for this SU and SL, right? So that all depends on the capacitor voltages of these two capacitor voltages, so this VC1 and VC2. So let us assume that so this VC1 and so VC2, right, is supposed to be maintain a voltage of V reference. Okay, so this is supposed to maintain a voltage of V reference. So that means this overall voltage is 2 times the V reference. The overall voltage is 2 times the reference. So that means individually they need to maintain V reference, but as a sum, so this also maintain 2 times the V reference. Okay, so VC1 plus VC1 equal to VC2, so it must be V reference, and at the same time the sum of these two must be 2 times the V reference. Okay, so based on these two constraints, the firing signals for this upper and lower switches will be generated. So first of all, see so how it will be operated. So let us assume that the voltage across this capacitor 1, that is the top capacitor, is higher than the voltage across the bottom capacitor. Okay, so for example, this voltage is greater than this bottom one. So what we have to do is we need to turn on the switch. We need to turn on this upper switch. Okay, we need to turn on the upper switch. So what will happen when you turn on this upper switch? So what will happen? Some of the energy in this capacitor is taken by this inductor, right? some of the energy in this capacitor is taken by this inductor circuit. So when you close the switch, okay, right, so how long it will close? So until, so this is equal to VC1, right, until this voltage is equal to VC1, we need to turn on the switch. Okay, so now this contains some energy, right? So whatever that excess energy that's stored in the capacitor, so that is transferred to this inductor. So now what we have to do is we need to turn on this switch. Okay, we need to turn on this lower switch. So that means that excess voltage is trying to charge this bottom capacitor. Okay, so that at some steady state point, so this both capacitor voltages, so VC1 and VC2 will be equal. There's simple logic, right? If the upper capacitor is having more charge, so the charge is transferred to the inductor, okay, and inductor, the energy stored in the inductor is now feeding the bottom capacitor, so that the capacitor means two capacitor voltages will be, until the two capacitor voltages equal will be equal. In similar way, if this upper capacitor voltage is greater than, so in that case this lower switch is turned on. So now the energy stored, some of the energy stored in this inductor, and this inductor energy is transferred to the capacitor. Okay, clear? So when you are operating this SU and SL, this external circuit, so the operation of this one is unaffected. So we are not do any changes in the rest of the circuit. So this external circuit is used only to balance the capacitor voltages. Clear? The operation is very simple. Okay, so there are two things. We need to maintain the two capacitor voltages equal, and at the same time the difference of these two capacitors, that is this VC1 equal to VC2, that must be equal to V reference, right, and VC1 plus VC2, that must be equal to 2 times the V reference. So based on these two constraints, so we need to design the switching sequence for switching operation for this upper and lower switches. So this kind of circuits, so where we are actually used, so this is what we discussed, right? Active power filter. So this is the external chopper circuit. So this one, this highlighted one, is the external chopper circuit. Okay, so this is used to balance these two capacitor voltages. So this is VDC1 and VDC1. So here this resistance RCH and LCH is a chopper resistance and inductance. So whenever this voltage VC1 is greater than this voltage, or if it is greater than the reference, right, so in that case the switch is turned on. Okay, so when this switch is turned on, so when this VDC1 is greater than VDC2, and when it is greater than the reference, so then the switch is turned on. Similarly, this bottom switch, so when it is turned on, so when this voltage is greater than the VDC1, and when its voltage is greater than the reference, so then it is turned on. Okay, clear? It's clear?
Yes, sir.
Clear? Do you have any doubts on this?
Yes, sir.
Okay. So now we'll try to design the switching sequence. So for this, so let us assume that these are the two capacitors. So we have these two capacitors. Okay, so assume this is C1, C2, and its voltage is VC1, and this is VC2, and we have this midpoint, and this is the remaining circuit on this right hand side. Okay, so we have this chopper circuit. A small resistor is connected just to charge this, just to make sure that the power is properly flowing in both the circuits. So let us assume that this SU and this is SL. Okay. Right. So as per our control circuit, so VC1 must be equal to VC2, and at the same time, so both must be equal to the reference. Okay. So what is our constraint? So when this VC1 must be, when this upper switch is turned on, so when this VC1 is greater than this VC2 and it is greater than the reference. So for example, there are two scenarios. Let us assume, right, example that. So V reference is 200. Okay, so V reference is 200. So that means VC1 must be equal to VC2. So that must be equal to 200. Okay, so first scenario, so assume that, so one voltage, for example, this capacitor voltage is 210 volts and this is 190 volts. Okay, so now, so which switch is turned on? So now which switch is turned on?
Upper switch.
SU.
So upper switch is turned on, right? Because this capacitor is excess charging, right? So somehow we need to transfer this excess charge, right? So therefore this upper switch is turned on. So that means this one is right. So now the question is, up to what point so we need to turn on the switch? Up to what point so we need to turn on the switch? So we have this reference, right? We have this reference. So we need to turn on the switch SU until this voltage it reaches to 200 volts. Okay, so you cannot continuously turn on, right? If you are continuously turn on, what will happen? This voltage is reduced to maybe at 195 volts, or it may be reduced, it is keep on reducing, right? But the second constraint is we need to maintain the two capacitor voltages equal. That means we need to maintain the reference voltage. Okay, so that means the upper switch is turned on, so until this 210 voltage so equal to this 200 voltage, that is the reference. Clear? Clear? Similarly, the second one, right? Similarly, the second one, for example, this voltage is second one voltage is 210 volts, and this is 190 volts. So this is VC2 and this is VC1. So now which switches we need to turn on? So which switch we need to turn on now?
Yes, sir. Lower switch.
So lower switch we need to turn on. So at what? So until, so how much duration? So we need to turn on. So until this voltage. So now as and when you turn on the switch, right? So the energy is transferred to this inductor. So this voltage is gradually decreasing, right? So this voltage, this VC2 voltage is gradually decreasing. So we need to turn on until its voltage reaches to 200 volts. Okay, so that means some steady state point, so both this difference, whatever the difference is there, right, so that will be gradually decreased at some point of time, so both voltages will be equal to 200. Okay, so now let us try to design the switching sequence. So we have VC1. Okay, so this is VC2, right? So now we are designing the switching sequence, or switching for the upper switch, right? So that means when it is greater than this one, right? So this is one constraint, we need to turn on the switch, right? So that means with this capacitor voltage is greater than this VC2, so in that case we need to turn on this switch. So up to what point we need to turn on? That is the second constraint. We have the second constraint, right? So what is that second constraint? So that is VDC1, right? So is greater than V reference. It's clear? It's clear? So we have two constraints. So VC1 is greater than VC2, we need to turn on the switch, and VC1 is greater than, so V reference, we need to turn on the switch, right? So that means, so in both conditions we need to satisfy. So that means we have this is the signal for the SU. Okay, it's clear? It's clear?
So
Okay, so for example, simple example, so let us assume that this capacitor voltage is 190 volts, one is 180 volts, and another one is 180 volts. But your overall reference is 200 volts. Okay, your reference is 200 volts, but these voltages are VC1 and VC2, so both are 180 volts and 190 volts and 180 volts. So under this condition, right? So what is the state of this SU? What is the state of upper switch?
On.
On, sir.
It should be on or off?
On,
It will on.
See here, right? See here, the main thing is the capacitor voltage must be 200, right? So that is the main criteria. So in this case, the first criteria is met, right? That means VC1 is greater than VC. See that this voltage is greater than this voltage, right? Okay, but we are not turning on the switch. So why we are not turning on the switch? Because this VC1 must be charged to 200, right? So this VC1 must be charged to 200. So that means we will not turn on the switch. Okay, so when will we turn on? So for example, this voltage is 210 volts and this is 190 or same it is 180 volts. So in that case, we need to turn on the upper switch. Okay, so already, right? So this is not excess charged, right? This capacitor is not excess charged, right? So in that case, so we will not turn on the switch. Clear? So this is the second constraint. The first constraint, from the first constraint, so VC1, this we will give, you will get 1 here, right? But in the second constraint, you will get 0. So that means the overall is 0. Okay? Clear? So simple logic that, so we have to, if the first capacitor voltage is greater than the second capacitor voltage, so that we cannot blindly turn on the switch. So we have other constraint. So that means that constraint, what that constraint is saying that, so that capacitor VC1 so must be equal to the reference voltage. Okay, so when both are met, so then only we have to turn on. So this is the second case. In the second case, so VC1 is greater than you got this +1. In the second case, this is this VC1 is greater than the reference. That means it is greater than 1. So therefore you will get 1 here. So that means the switch is now on. Okay, so how long it will be on? Right, so this capacitor voltage, this 210 volts, is gradually decreasing, right? At certain point of time, we have this V reference, right? So when it is greater than V reference, that is when it is when it is less than 200, so at that point, so this will become 0. So now the overall output will be 0. Clear? It's clear? Okay, so this is the switching for SU. Similarly, for switching for S lower, so how it will be? So for S lower, we need to compare the two switches. So this must be now, this is VC2 and this is VC1, right? Agree? So we have the other constraint. Okay, so we have this other constraint. So now this is VC2 and this is V reference. So this is for the S lower. It's clear? It's clear? Okay. The same theory is followed here. So when this capacitor 1 volt is greater than, when capacitor 2 volt is greater than the 1 voltage, right? So we need to turn on the switch. So when only, so V reference is greater than the VC2. It's clear? It's clear?
Yes, sir.
Yes, sir.
Okay, so this is how we will operate this upper switch and lower switch. So remember, these SU and SL are not complementary. So this SU and SL are not complementary. The idea is simple, right? So in one way you are feeding that means one, so whatever that external that means excess charge is there, right? That excess charge is transferred to the inductor, right? And it is feeding to it is charging to the bottom capacitor, right, or bottom DC source. So when this is excess, so that is feeding to this capacitor or this bottom capacitor via this inductor. Similarly, when this bottom capacitor is excess charge, so that is feeding to the upper capacitor, so via this inductor. Okay. So by appropriately turning on the upper and lower switch, so we can obtain the balance. It's clear?
Sir, what happens when both upper and lower switches are turned on, sir?
So when both turn on, right, the source will be short circuited, right? This capacitor, two capacitors will be short circuited, no? So this condition will never occur, right? So if you use this logic, so this condition will never occur. Okay.
Sorry, you said that S upper and S lower are not complementary. No?
They're not complementary, right?
Then
So that condition will never occur, right? Only one switch we can always on, right? So we have this condition VC1 and VC2, right? Okay. So at that condition, you have only one switch is turned on, right? Either upper will turn on or lower will turn on. So we have always this VC1, VC2 are there, right? Okay. If this VC1 is greater than this one, so there is a chance that this upper will be turned on. If this VC2 is greater than, so there is a chance that the lower will be turned on. Okay.
okay.
So if at all both are same, so in that case the second constant is also there, right? So that means there is a chance that both are 0, but there is no chance that both are 1. Okay.
Okay.
Yeah.
Thank you, sir.
So this is so how to implement this capacitor balance. So when you use an external circuit, so this is what the results are obtained. So in this specific case, right? So this is the point where the capacitors are unbalanced is there, right? So because one capacitor voltage is trying to reduce and the other capacitor voltage is trying to increase. Okay, so overall it is maintaining constant. Okay, but one capacitor voltage, if it is continuous, right, this capacitor voltage will be reduced to 0 and this capacitor voltage is still increasing. Okay, so now this is the point where I turned on this chopper circuit. So this is the point where I turn on the chopper circuit. You can see that so both capacitors are balanced, and moreover, so they are maintaining the reference voltage of 200. Maintaining the reference 200.
Sir, they cannot charge and discharge simultaneously, sir. There will be some gap.
They
Like
cannot charge and discharge.
both one cannot charge at a time and other discharge at a time, sir. There will be some time gap that after one is discharged,
So
the
only
other
one is charging, right? Only one is charging. So that's why still you are getting some ripples here. Some small ripple content is there, right? See here. Okay, some small ripples are there, right? Okay.
No, sir. The confusion is according to this graph. It is showing like both are charging and discharging at the same time, sir. That is the confusion.
No, they are not charging and discharging at the same time. If you are properly, then how it will form a chain like stack. If this capacitor is charging like this, so other capacitor is charging like this. Okay. So generally it will form a chain like structure. Okay. If you zoom it properly, you can see that some chain like structure. So this is the capacitor is charging, and at the same time this capacitor is discharging. Okay, discharging and discharging.
Okay, sir. Got it.
So both will not simultaneously charge, right? So in diode clamp only one capacitor, either the upper one or bottom one will charge. That all depends on the current direction. Okay, so this is capacitor balance. So with using some external circuit. So when you use some external circuit, right? So this is the another one. Okay. So another variant. of this this one. So what is the difference between the main diode clamped inverter and this circuit? So what is the difference?
Diodes are replaced by active switches.
Yeah, these diodes are replaced, right? So earlier we have these diodes, right? Okay, now these diodes are replaced with the active switches. It's a switch with a anti-parallel diode, a switch with a anti-parallel diode. So what is the drawback when you have only diodes? So in that case, we cannot control the current, right? So that means the current will be forcefully. That means if you have only diodes, right? If you have only diodes, the current flow either in this direction or in this direction, right? Okay. So for example, if you want to discharge this capacitor, okay, if you want to discharge this capacitor, you need to run this one in this direction. You have to work, right? So, but the diodes are not allowing to operate. So that means the capacitor is still discharging, right? That means the even if you are to charge the capacitor, but you are not trying to means you cannot charge the capacitor because the diodes are not allowing to do. Okay, so that means the capacitor voltage is still, and again it is discharging. To replace that, what we have to do is what they done is this diode, this now it is replaced with the active switches. So that means we have two current flows. So that means the current will flow in this direction, or that means the current will flow through this switch, or this current flow through this diode. So now we have option, right? So now we have option so that we can balance these two capacitor voltages. Similarly, in the bottom one, so the current will flow in this direction and the current will flow in this direction. So that means this capacitor can be charged or discharged by appropriately routing the current. So this is known as active neutral point clamp or this active DC MLI. Okay, so this requires two additional switches, right? So that means overall how many switches are required for 3-phase? So how many switches are required? 6 switches are required, right? So this is 1, 2, 3. So earlier case, in this case, you have only 2 switches are required. So only 2 switches are required along with some small inductance and some resistance. Okay, anyway, this resistance is normally not externally included. So whatever this inductance is having some resistance, right? Practically, it's having some resistance. That resistance, that means you can simply ignore this one. It requires one inductor, one small inductor, and 2 switches. So whereas this one, this active neutral point, it requires 6 of such, right? That means 4 extra you require. So 4 extra you require. But the good thing is the diodes are absent, right? So the diodes are now absent. Yeah. So this is active neutral point clamped. So this is active neutral point clamped. Yeah. So this is another one. So this is off leg T type. So this is off leg T type. So these are the alternatives for the diode clamp. So first one we see in that diode clamp with external circuit, and also we see in that active neutral point clamp. So that means the diodes are now replaced with the active switches, and this is another variant. So that is off leg T type. So this is off leg T type. So here this operation is simple. So we have only one switch here. Okay, top we have one switch. So bottom you have another switch, and this is a bidirectional switch. You might have studied this, right? Bidirectional switch in APC course. Okay, this is known as 4-quadrant switches, bidirectional switches. So what it has basically do is, so this is unidirectional, right? So it can block voltage in one direction, but it will allow the current in 2 directions. It can block voltage in one direction, but the current flow in this direction when the switch is conducting, and in the opposite direction when the diode is conducting. Okay, but it can't block the negative voltages, right? So whereas this one, this is a combination of two IGBTs with anti-parallel diodes that are connected in common this configuration. So this, what it will do is it can block the voltage in both directions. Okay, it can block the voltage in both directions and allow the current in both directions. Okay, so allow the current in both directions. So these are known as bidirectional switches or 4-quadrant switches. Bidirectional switch or this 4-quadrant switches. Okay, so now the question is, right, so this is a 3-level, right? So this voltage is VDC. Let's say assume that this voltage is VDC and this voltage also VDC. Okay, so for example, if you want a voltage between A to 0, you are measuring the voltage between this A and 0. So how to get VDC voltage? So which switch we need to turn on? If you want VDC voltage between A and 0, so which switch we need to turn on? So which switch we need to turn on?
S1A and S3B.
If you want a voltage between this A and 0, so we need to turn on this S1 here, right? So as and when you turn on this A, so this A is connected to this positive plate and 0 is connected here, right? So that means VA0 voltage is VDC. Okay. Similarly, if you turn on this bottom switch, so what is the voltage? If you turn on the bottom switch, so what is the voltage you will get across A and 0? So if you turn on the bottom switch, so this A is connected to this 0 or this negative. So that means this voltage between A and 0 is minus VC. It's clear? So we are measuring the voltage between this A and 0, this point and this point. So when you turn on this upper switch, okay, now this A is connected to this point. So that means this voltage is VDC. So if you assume both are same, VDC. Similarly, when you turn on this bottom switch, so in that case, what will happen? The voltage between A and 0 is minus VDC. So VDC minus VDC. So now we have 0 level, right? So for 0 level, so which switch we need to turn on? So 0 level between A and 0. So which switch we need to turn on?
S2A.
For 0 level, right? That means this A must be connected to this point. So that means we need to turn on this switch S2A. So we need to turn on this switch S2A. So remember the gating pass, these are two IGBTs are there, right? So gating pass for two IGBTs are remain same, but only one IGBT will conduct. So depending on that means. So for example, this current flow is like this. We have some slides. Yeah, just we'll briefly review the bidirectional switches. Okay, so bidirectional switches are 4-quadrant switches. So these we have unidirectional switches. So that means the switch with anti-parallel diodes, that what we have seen, right? So bidirectional switches that can block the voltage in both direction and it will allow the current to be conducted in either direction. Okay, so right now there are no bidirectional switches are available, but there are some possibilities so that can we can form a bidirectional switch. So this is one way to provide a bidirectional switch. Okay, so that means here, so 4 diodes, it will form a bridge-like shape, and inside that you have one IGBT. So it can block the voltage in both direction. So it will allow the current in, for example, if the current is positive, current is flowing in this direction, so it will flow through this diode and through this switch and through this, something like this. Okay, so this is the direction for the one means positive current. So if it is a negative current, so that means that case these two diodes are turned on. That means these two diodes are conducting, so along with this switch. So that means the current direction, it will be something like this. It will flow in this direction, so this dotted direction. Okay, across the switch, the current is always in one direction, but depending on the current direction, the opposite diodes will be conduct. So how many switches are actually conducting here? Two diodes and one switch is conducting, right? So depending on the current direction, so two diode and one switch is actually conducting. So two diodes are conducting and one IGBT is always conducting, right? So two diodes and IGBT is always conducting. So we have other one. Okay, so this is two anti-parallel diodes, two anti-parallel IGBTs with anti-parallel diodes are connected in series, right? So we had two different configurations. One is the common emitter and common collector. If you notice that, see here, this is emitter, right? So this is emitter. So this is also emitter, right? The emitters are common here. So whereas these collectors are common here. See here, these arrow marks are, if you notice that these arrow marks are connected, right? This is emitter, right? For this IGBT. So this is the emitter. So this is common emitter. So whereas this is the collector, right? So this is emitter and this is collector. So collectors are common here. So one is the common emitter configuration and another one is common collector configuration. So which one is normally preferred? So which is preferable choice, common emitter or common collector? Which is preferred?
Common emitter.
Common emitter is preferred or common collector is preferred? Or I will ask you, so how the gate is actually connected? How the gate pulse is actually connected? Where it is connected in IGBT? So where the gate is actually connected? Gate signal is connected between what terminals? We have three terminals, right?
Gate and
Collector, emitter and gate. So where exactly that gate is connected?
gate and emitter.
So gate signal is connected. For example, this gate signal is coming, right? So where exactly this is connected? So gate and what is the other terminal? Collector or emitter?
Emitter.
Emitter.
Emitter, right? So gate signal is connected between gate and the firing signal is connected between this gate and emitter. Okay. So now, right. So here this emitter is common, right? So this emitter is common to these. So therefore, you require only one driver circuit. You require only one driver circuit for this. So whereas if you have common, common collector, so in this case the collector is common. So that means we need to connect. This is gate, right? So this is gate. So we need to have two driver circuits. So one driver for this upper one and one other driver for this bottom one. It requires two driver circuit as their emitters are separated. So whereas this emitter is common, so therefore you require only one driver circuit. So now the current flow, right? So that if it is a positive, if the current is flowing in this direction, so that means the current is flowing through this switch and through the diode. Or if it is the current flowing in the opposite direction, so in that case, the bottom switch IGBT and the upper diode. Okay, the bottom IGBT and upper diode, so the current flow will be there. So that means at any time, so one switch is conducting and one diode is conducting. So we reviewed three types. So one is the bridge type where we require one IGBT and four diodes. So in that case, two diodes are conducting, two diodes and one IGBT is conducting. So whereas here on this common emitter and common collector, one IGBT and one diode is conducting. But there is an advantage when you use common emitter. So the specific advantage, that is, it requires only one gate driver circuit. And remember, the firing pulse for this upper switch and so bottom switch will be same. So whereas in common collector, so you require two driver circuit. So that is what it's mentioned, right? So however in common emitter, so one gate driver is sufficient to drive both IGBTs, but see common collector, so that requires two gate drivers. Okay. So whereas now these bidirectional modules also right now that are available in market. So this is the symbol for a bidirectional switch. Okay, so this is the symbol for a bidirectional switch. So there is one additional line is there, right? Some additional line, so that represents the bidirectional switch. That is a symbol for the bidirectional switch. Actually, these bidirectional switches are not used in matrix converter. So matrix converter is a direct AC to AC conversion. Like your cycloconverter is there, right? So cycloconverter, they use thyristors. Okay, so thyristors having some limitations. So especially you cannot go for different frequencies in the output side. So therefore we have this matrix converter. So in matrix converter, these bidirectional switches are used. And these are the different manufacturers, okay, that use these bidirectional switches. So there is UPIC, Exis, Fusey, Semicron, and this Semilab, Dynex. So these are the different, and this is the configuration. This is common collector. So DB means diode bridge, and this RB IGBT is the reverse blocking IGBT, right? So this is known as reverse blocking IGBT. Reverse blocking IGBT. So that can block the voltage in both direction and allow the current to be conducted in both directions. This is reverse blocking IGBT. So this is common emitter, and these are all okay. So this is especially used in matrix converter. So we have these configurations: common emitter, common emitter. See, if you notice that most of them we use common emitter except this first one. Okay, we come to our actual discussion. Yeah. So this is what we are discussing, right? Okay, if we want 0 voltage, so we need to turn on this switch, right? We need to turn on this bidirectional switch. So depending on the current direction, so either this IGBT will conduct along with this diode, or this IGBT will conduct along with this diode. Okay, so that means we have the flexibility is there, right? So we have some flexibility is there, right? That means we can control the current, so based on turning on the switch. So that means we can balance the capacitor voltages. And moreover, if you compare with the diode clamp, right? So how many switches are required for diode clamp? How many switches are actually required in case of 3 level? If you compare with 3 level, right? So how many switches are required? 1, 2, 3, 4, right? So 4 switches. So this is another 4. That means 4. So 12 active switches and 6 diodes you require, right? 12 active switches and 6 diodes you actually require. So whereas in this case, so how many switches are required? 18 switches are required. 18 switches are required. So whereas how many switches are required? 1, 2, 3, 4. So 4 switches. That means 12 switches are required. That means the 6 whatever that anti-parallel diodes are there, right? So those are not required. And moreover, the driver for this one is one driver. You have, if you count on the drivers basis, you require one driver here. 1, 2, 3, 4, 5, 6, 7, 8, 9 drivers. 12 switches are required and 9 driver circuits are required. So comparatively, the cost will be very much reduced, and moreover, the switching losses is also reduced, right? In case of 3 level, that means diode clamp. So in this case, right? These two switches are conducting, right? If you want VDC voltage or this voltage, these two switches are conducting. So whereas here only one switch is conducting, right? For VDC voltage, only one switch is actually conducting. So that means the losses is also reduced. So at any time, only one switch is conducting. It's clear? Okay. So this is about off-like T-type topology. So these are the alternatives for the diode clamp. So why it is all these are required? Because some drawbacks are there in the diode clamp. So especially so that doesn't have any switching redundancies are not there, and the whatever the current that flow in the neutral point, so that is always unidirectional. So therefore, so these will address to some extent. Clear? If you have any doubts, you can ask me. If you have any doubts on here, this. Okay, if you have no doubts, I will stop here. Okay. Okay, na?
Okay, sir.